Hello, Akhil sir.
Yeah, yes, ma'am. Shall we start?
Yeah, sure.
So, good evening, all. So, for the second session today, we have with us Dr. Shreelakshmi MP, Assistant Professor in the Electrical Engineering Department at NIT Calicut. She holds an M.Tech PhD in Power Electronics and Drives from IIT Bombay. So, her doctoral research focused on energy efficiency, power quality, and reliability improvement of induction motor drive based passenger elevator systems, addressing real world industrial challenges. So, Dr. Srilakshmi has made significant research contributions in the area of power electronics, motor drives, high gain DC-DC converters, ultra-capacitor energy storage systems, and electric transportation. She has multiple granted Indian patents, including patented solutions for energy optimal motor drive control and active voltage balancing of ultra-capacitor banks. She has published extensively in high-impact IEEE journals, including IEEE Transactions on Industrial Electronics, Power Electronics, Industry Application, and Transportation Electrification. She has also led and contributed to major funded projects from agencies such as DST, SERP, NIOT, and has handled industrial consultancy projects with organizations like Tata LXI, SFO Technologies, and Sunpar Industries. Dr. Srilakshmi is a recipient of the prestigious DST Inspire Award and was recognized as Woman of the Year in Power Electronics by Niti Aayog. With her strong blend of academic excellence, industry engagement, and impactful research, we are privileged to have Dr. Srilakshmi MB as today's resource person. So, on behalf of GC Kannur and FTP coordinator team, I welcome Dr. Srilakshmi MB for the presentation. Welcome, ma'am.
Thank you, sir. Shall I share the screen?
Yes, ma'am. Yes.
Yeah. Are you able to see the screen?
Yes, ma'am.
Yeah. I'll just put it in the full screen. Yeah. Are you able to see it clearly?
Yes, ma'am.
Now is it? It is better, right?
Yes, yes.
Yeah. Okay. Fine. So a very good evening, all of you. I hope you had an introduction to supercapacitors from the previous session handled by the Geltron experts. So the Geltron is one of the manufacturers of supercapacitor, and I also got a chance to visit that manufacturing facility, and it is a very attractive thing as far as the researchers and the people working with supercapacitors are concerned, as we have a facility in our own place. Not only when we say as a nation, but as a state also, we have a facility which makes supercapacitors, and the characteristics what we find for those capacitors can match with some of the supercapacitors which we have imported in our lab. So it is a very tedious process for manufacturing, and it is very good that we have come up with the production center for that. So what we do, you might have understood what is a supercapacitor, but what we do as power electronic engineers here, and also as people who work closely with drives or electric vehicle technologies, we try to make use of these supercapacitors, or how we can use the characteristics of this wonderful characteristics of the supercapacitors in order to make it into some application which is having a lot of benefits over the other storage units. Okay, so we have tried with various schemes for supercapacitors, and the best scheme as of now is a hybrid storage where we have both supercapacitors and battery in the whole system. But then there can be storage which is made only with supercapacitors also. There can be storage which is having a larger proportion of battery and a lower proportion of supercapacitors, and so on. So all of these have its own benefits and its own disadvantages. So we will see first how we can use supercapacitors as an alternate for the storage units as such. Okay, so we'll just see one way in which we had tried to use supercapacitors, not a hybrid. So though our theme of this presentation is a hybrid storage, first I will just introduce you to storage which can be developed only with supercapacitors. And then we will see what are the shortcomings of that from the technology available till date, and then how we are trying to overcome that by making it as a hybrid, and how we can make it as a hybrid. Okay, so that will be the flow of this presentation. So especially for electric vehicles and all, we had through one of the projects which we had done here, proposed the use of supercapacitors in order to ensure that there is fast charging, as the main issue with the adaptation of electric vehicles is the charging time. Okay, so supercapacitor, hope you may be aware. So this is just an evolution of electric vehicles, and we have electric vehicles from starting from 1800. It is the first electric vehicle, and then even now we have that. And these are the various charging strategies. So we know that even now the fastest charging will take at least half an hour to charge a vehicle. So that is not because of the limitations of the charging infrastructure. The charging infrastructure can deliver any amount of current to charge the battery or whatever storage we want it to. The charging infrastructure, even though from the point of view of implementation and all, it may have certain limitations, but theoretically there is no limitation for the charging infrastructure. But the limitation comes from the battery side, because I hope you all know how a battery is getting charged, right? So when we say it's a 100 ampere hour battery, when we deliver 100 amperes current for 1 hour, it gets charged. Same is the case while discharging. If it is giving out 100 amperes for 1 hour, it is completely discharged. Okay, so it is basically the current which will charge a battery, right? So when we try to decrease the charging time, what we are trying to do is to increase the current. Okay, so suppose we want to charge this 100 ampere hour battery in 15 minutes. The only thing we have to do from the charging infrastructure point of view is to deliver a 400 ampere current for 15 minutes. So if you give 400 ampere constant current for 15 minutes, it gets charged fully, right? So if you want to even make it 7.5, you just have to give it 800 amperes. So giving out 800 amperes, even though it looks like a very huge current, is not a problem from the charging infrastructure point of view, because it is off board. It is not inside the vehicle. It is an outside station, and we can make it as big as what we want, and it is not having any kind of limitations. We can have a different substation for it, and all those things can be managed, right? But then the problem here is with the battery side. What is the problem there? A battery, how does a battery gets charged? Anybody? Do you know? What is the process through which a battery stores energy? Am I audible?
Yes, ma'am. Okay.
Yeah. If you are elected to talk, you can even drop a message, which I hope I can see. So a battery, it usually gets charged by what is called as an oxidation reduction chemical reaction. And when we are supplying more electrons, we are trying to increase the rate of these reactions. That is a reaction. The number of reactions to be completed in 1 second is getting increased. Okay. So when we give, say, higher and higher current, we are making more and more number of reactions occur in lesser number of time. Sometimes all these chemical reactions have its own time to complete. So when we make it very fast, what happens is if it is not capable to complete the reaction in that the chemicals used is not capable to finish the reaction, it takes more time than what we demand for the reaction to be completed. What happens is there will be a lot of incomplete reactions, which will lead to a lot of residues. Okay, so this is just because it is a chemical reaction, which is oxidation and reduction. Now, when we come to a capacitor technology, a capacitor stores energy not by chemical reaction, but by polarization. So that is the main difference now. A polarization means there is nothing, no reaction happening. It is just the separation of charges. And how fast it can be as fast as the speed of light because it's electron which is moving, right? So it is very fast as compared to that of a battery. And there is no problem in demanding the number of reactions or number of electrons being transported, or increasing that number of electrons. That demand has no problem on the life cycle of a capacitor. Okay, so that is why a capacitor is suitable for a higher power delivery and a battery is suitable for higher energy delivery. Okay, so the capacitor, because of its play arrangements and all, it has limited value for the capacitance. So the storage energy is limited when compared to a battery. That's why it is supposed to have a higher energy, higher power density, but a lower energy density. So in case we want to reduce this level 3 fast charging time to a very low value, say 10 minutes or 5 minutes, that is the time we take to fill in the petrol tank and come out of a gas station, right? So if you really want to get into that kind of a convenient state, then we would really want these reactions to happen at a very, very, very fast rate. And the battery technology available till date has not been capable of doing it. Okay, so even though you make a very good charging infrastructure with the batteries available nowadays, it is very difficult for making it charge very fast. It will actually affect its life cycle. Okay, so the only solution is to switch to supercapacitors, which is capable of fast charging. Okay, so how we can charge a battery or a supercapacitor is there are what I told now is a constant current charging method, which is we are supplying a constant current and then amount of current decides the charging time. Then there is also constant voltage charging. It is a very slow charging, but it has very the efficiency wise it is low, but then the better thing is that because we are controlling the voltage, there can be more current flowing and it is very easy to enable the fast charging. Then there is a combination of constant current and constant voltage. This is what is mostly preferred for charging, where until certain SOC, state of charge value, it is a constant current being given, and then later on it goes to a constant voltage. Okay. There can also be multi-stage charging where the value of the constant current being fed to the battery can be changed over the time based on the state of charge, and because of that, the battery life cycle can be slightly improved over the previous constant current charging. And this is one of the other very much used charging method, which is pulsed charging, where the current goes to zero in between. That actually helps in cooling out. So whenever we talk about a fast charging mechanism for a battery and all, or let it be for a supercapacitors or for any such systems, the main issue is that being higher current means higher copper loss, higher heating loss. Therefore, there needs to be a better cooling method. So the air cooling mechanism for such storage units may not work. It may need some kind of water cooling or forced air cooling or some other phase changing materials or many sophisticated mechanisms for the cooling, because if the temperature goes high, then the behavior of the complete system would change. Okay, so then came this method of pulsed charging, where the current is whatever is the current being given is given as a pulse, maintaining the average value to the required value. Okay, so the charging time is not affected as it is a pulsed current, but then what is the gain is that there is, after a huge current there is a zero current. So the benefit is that we will have some time for the cooling of the batteries. Okay, so this mechanism is actually helpful in the heat dissipations and all. Okay, then after reaching a certain state of charge, if you keep connecting the battery to the charging unit, what it does is a trickling. So whatever is the self discharge which is happening in the battery or in the other storage unit, it will just take that much only current to take it to always 100% SOC, and that is called as a trickling. And this trickling actually helps in improving or making the whole charging process as trickling actually helps in making a better life cycle. Okay, so what is the best charging method here will be to use the slowest one. Okay, so whatever be the battery type and the capability, if you charge it at the slowest rate, it is supposed to improve the life cycle of such batteries. Okay, so the slowest is the safest, but then it may not be what we want from the application point of view. That is why we may not go for the slowest always. So then we should choose a current value which the battery or the storage unit can tolerate. Okay, only then it will be capable of doing that. Okay, so what are the alternate storage methods available for electric vehicles other than the batteries? So we can also think of having ultracapacitors or supercapacitors. As I said, first we will see how we can use them as a sole energy source for the electric vehicles. And then we can also have flywheels. Then we can also have fuel cells inside for the vehicle. Fuel cell, though it's not a storage, the storage being hydrogen, it is just a mechanism of fuel injection. But then still, it is the storage will for the fuel cell will be hydrogen-based storage. Okay, so all these have its own benefits and all, but the one storage which can directly replace batteries in such applications are supercapacitors. Okay, so we'll just see how these different batteries are used. These are the different batteries are used: lead acid, nickel batteries, or lithium batteries. So they have their own pros and cons, and based on that, most of the times it is the lithium-based battery which is preferred every time. Okay, and then as I said, the battery, when we charge it at a constant current. Okay, and the number of cells of a battery. I hope you know that the battery is made up of many cells. They are connected in series and parallel to make the battery. Okay, so the number of cells will decide the voltage rating of the battery. So normally a cell cannot have a voltage rating more than 3 to 4 volts. Therefore, if you want a higher voltage rating, that many cells have to be connected in series. And then for a higher energy density, that series string has to be repeated in order to increase the total energy capacity of it. Okay, so if you see here, you can see that the batteries, what is used, let's take the pointer. The batteries, what is used, the battery pack has so many cells. See, why this is relevant is this is the same case for supercapacitors as well. Now, when we are trying to use a supercapacitor as a storage unit, we may have to give a supercapacitor of a voltage rating which will match the voltage rating of the system. Okay, so let us assume that the supercapacitor cells manufactured nowadays can have at least maximum of 3 volts. Okay, so as I said, a higher current is not going to affect a supercapacitor being a capacitor, right? Because whatever be the rate at which you demand the separation of electrons, it can do that. That is because it is polarization. No chemical reaction is there. But what would affect its lifetime or life cycle is the volatile nature of the electrolyte. Okay, so there is an electrolyte which gets volatile if you apply a voltage which is more than the rated value. So if a 3 volt supercapacitor is exposed to a voltage greater than 3 for a longer duration, then what will happen is that its electrolyte gets volatile and then it gets damaged. Okay, so the only restriction when we use a supercapacitor is that the voltage cannot be more than the rated value. Okay, so what we do here is we will try to make the voltage less than the rated value. So for that reason, what you do, suppose you want a 300 volt battery supercapacitor bank, and the voltage rating of individual supercapacitors is only 3 volts, right? Then what do? You will have to connect 100 such supercapacitors in series so that a total of 300 volts, individually 3 volts distribution is there, right? So therefore, there is a requirement of a lot of cells connected in series in order to make a bank having this voltage rating which can match the voltage requirements of the system. Okay, are you with me? Okay, so so that is one thing when we use supercapacitors as a bank. Then so when we are doing that, we face certain problems. That is one thing which we can discuss, and what we'll see that. Before that, let us also see this plot. This plot is very important. Maybe you might have seen this in the previous presentations. It is called as the Reagan plot, which is the plot between the power density and the energy density. Okay, so an ideal storage will always have a graph somewhere here. It should have very high power energy density and a very high power density. That should be the way a ideal storage should behave like. Okay, now where is battery? A battery is having a very high energy density. It has a very high energy density. You see here, lead acid battery, nickel cadmium battery, lithium ion batteries. They have very high energy density, but lower power density. Okay. Now take the case of a capacitor, it is having very high power density, but very low energy density. So what we want is both these to go to this place where a capacitor, if you look at a capacitor, you want the energy density of a capacitor to be improved. Or when you look at a battery, you want the power density of the battery to be improved. Okay, now supercapacitor comes somewhere here in between where the energy density is not that high. This is the energy density of battery, but it is not that high as that of the battery. Suppose this line marks the energy density of the battery. The energy density of supercapacitor is here. So there is a difference. But the power density wise, it is much better than that of a battery, right? So it is going towards what we assumed place for the ideal storage. It is moving towards that. So how it is capable to do that is because of the activated carbon and the nano and plates and all those things. Okay, so supercapacitor, being a capacitor, can deliver higher current or can take higher current without affecting the life cycle. But being a capacitor of a higher capacitance, higher energy density, it can also handle energy which is much, much larger than an energy handled by the normal electrolyte capacitor. So that is why we call it as a super capacitors. Okay, so when you compare it with a battery, if you see the energy density wise, it is all the battery which is going to win. When we look at the self-discharge rate, it is more for the supercapacitors. That is not a good thing. It is a bad thing, because what does it mean? If you keep a supercapacitor charged and then after 1 month, you don't connect any load to it. After 1 month, we come and check the state of charge. For a battery, it might have discharged, but a little bit. But supercapacitor might have become half by that time. Okay, so that is because of the self-discharge. So the self-discharge rate is more for the supercapacitors. It's not a good thing. Then power density wise, the supercapacitor is a winner. Charging, discharging speed is supercapacitor is a winner. Life, supercapacitor has much, much, much larger life than that of a battery. Maintenance is very less for the supercapacitors, and there is higher temperature range for the supercapacitors. So for all other things, other than the energy density and the self-discharge rate, it is a supercapacitor which has a upper hand. But these two are also very important. Why? Because when we say it is a storage, we don't think about a short-term storage. We may use batteries as a long-term storage also. So if it is not capable of that, then it is a limitation. That is why we prefer to go for a hybrid kind of a storage. Okay. And also energy density wise, what does it mean? If 1 kilogram of a battery can store some amount of energy, that is, it can light a lamp for say 5 hours. When I'm just talking in terms of weight, so that you can relate to it. But then for the same lamp to light for 5 hours, I may have to use a 3 kilogram of the supercapacitors. So energy density, energy per kilogram is more for the battery, less for the supercapacitors. So the size, the requirement will be, the weight requirement will be more for the supercapacitors. Okay. So these are the main issues with respect to the supercapacitor, which needs to be handled. Okay. Now, when you see the supercapacitors, as I said, now the main issue is one, as I said, there is energy density and all, and self-discharge rate. More than that, there is also voltage rating, which has to be very, very strictly followed. Now, when you connect many supercapacitors in parallel, in series, to increase the voltage rating, then what is the problem coming in? Suppose we connect 5 supercapacitors. in series like this and say we give a 5 volt here, what we expect is that every capacitor to have 1 volt, assuming that they all have the same capacitance value. This is the distribution we assume it will have, but it will never have this kind of a distribution because the capacitance is varying by a tolerance of plus or minus 20%. That is, if it's a 1 farad capacitor, the variation can be from 0.8 farad to 1.2 farad. So some of the capacitors will be say 1.2 farad, some of them will be say 0.8 farad. So what will happen? Then because of that, the voltage division will not be uniform. Lesser capacitance will have a higher voltage, the lower capacitor will have a lower voltage. See, it will be like this. So suppose we are utilizing it to the maximum. Say I'm instead of giving 5 volt, I'm giving 15. So each of this were expected to have say 3 voltage like this, 3 volt. But then what happened here, because of this non-uniform super capacitance value, the other one, this will have say 2.8, but this will have 3.2. Now this 3.2 volt is something which is a difficult thing for us because it will affect the life of this capacitor cell. Once the life of this capacitor cell is affected, the whole string of capacitor gets affected, right? And therefore it gets damaged. So what will then, what is the possible solution then when we see that there is a division where if something is going beyond the expected value, then only way without any change in the whole system, what we can do is to only give say 12 to 13 volts, so that all these voltages will be less than 3 volt. That is one solution we can do. Then what we are doing? We are underutilizing the string. Or what we can do, instead of having 5 cells for 15 volt, make it 7 cells such that no cell will have a capacitance, have a voltage more than 3 volts. That is also, then again it is underutilization of the string. So, so when we make a supercapacitor bank as such, with the imbalance in the voltage, because of that, it will either lead to over voltage, which will lead to the damage of the supercapacitor, or if you are trying to avoid this over voltage by increasing the number of capacitors connected in series, then you'll end up having a underutilization of the string. Okay, so what will happen when there is a prolonged exposure to over voltage is it will get aged faster. So there can be bulging, increased ESR, capacitance loss. Then there can be venting, electrolytic decomposition, gas generation. All these are possible, which where what will happen ultimately is the entire system may get failed. Therefore, what is required is to have a balancing, voltage balancing when we try to make a supercapacitor bank, and that is very critical. Okay, so supercapacitor can be used as a sole energy source by making the voltage rating of the supercapacitor match that of the system voltage by connecting many cells in series, just as we do for the battery. But the only thing is, if you want to match the energy density, the weight of supercapacitors will be very large. Okay, so when we think of these kind of solutions, as I said, because energy density is very large and the self-discharge rate is also very large, people tend to think that we may the use of supercapacitor as a sole energy source is not very good. But that is okay in certain scenarios. So I'll just tell you one scenario where we have done this, the use of supercapacitor as a sole energy source or a sole energy storage. That is for the vehicle which will have frequent stops like a city bus or maybe a campus vehicle where there are frequent stops, and then the vehicle will stop also at a predefined location. Okay, so then because if supercapacitor is capable of very fast charging, if you just place it at if you place the charging stations at the locations where the vehicle is supposed to stop, and if there is any touch and brake arrangements made where the vehicle gets charged while the people uh, comes down of the vehicle and get into the vehicle. Approximately it is around 20 seconds to 1 minute time, which is taken according to the crowd. Okay, so we'll take the least being 20 seconds and the highest being 1 minute. So in that duration, if you supply a higher current, the supercapacitor can get charged. Unlike battery, it is not going to affect the life cycle. It is not going to affect maintenance or anything for the supercapacitor. Therefore, we can do that, and then the energy what it requires will be energy only to transport from one stop to the other, not for a complete range, right? So the range will be very less required by the storage. So if you do a calculation in that way, the weight requirement of supercapacitors comes down by 1/20th of that what is required by a normal vehicle. Okay, so that is the benefit what we get by using a supercapacitor. But then we cannot use it for a highway transport or for a vehicle which is supposed to run for a whole day with one single charge. Say we expect a vehicle to run for 150 kilometers, 200 kilometers a day, and only after that we have a provision to charge. Then if you are trying to use a supercapacitor instead of the battery, the weight of the supercapacitor will be 3 times to 4 times more than that of a battery, which will be difficult, right? So only for systems where we have predefined stops, when there is a possibility of frequent charging, we can use supercapacitor as a sole energy source. Okay, so that is one part. Then what way we can improve it is by making it a hybrid storage. That is when we have supercapacitor as well as battery both together. Okay, so how we will connect this? We have both of them is expected to have the same voltage rating. So we have the supercapacitor bank, and then we have battery bank, and what we do is to connect them in parallel. Let's show you. Can connect them in parallel like this. Okay, to a load. So this is hybrid. Now, if suppose there is some current requirements by the load, say I1 plus I2 is the current requirement by the load, then a part of it, say I1 will be given by the supercapacitor, I2 will be given by the battery. So there is a sharing of load. Now, the percentage of sharing of the load can be controlled if you keep converters here for interfacing the battery and supercapacitor and regulating these currents such that always only the current what we expect the battery or the supercapacitor to deliver will be delivered. Okay, so such hybrid units of supercapacitors and batteries are very popularly used in cases, most of the cases, where the supercapacitor will be providing what is called as the surge requirement, that is, and the battery will provide what is the nominal value. Okay, suppose what is a example is let us take a motor. If you see the starting of a motor, it takes a very large current during starting, then it comes down to a nominal value. Okay, so this nominal current, say let us assume that it is a say 1 HP motor or so, and it is full loaded. So let us assume that this is say around 4 ampere current, but this one may become around 12 amperes or so. Okay, So what is this 12 amperes, if you're trying to take it from a battery, the same issue like what we said before will happen. What is the problem? Battery trying to deliver a larger current will try to increase the rate of deoxidization reaction, right? So what the battery, what it will do? There will be the rate of reactions will be here. It is increased 3 times, which sometimes the battery chemicals may not be capable of. Then what? There will be a lot of residues inside the battery. Those residues are going to affect the life of the battery. So more the time you take the such kind of a peak current, the battery life is getting trying to get deteriorated. Otherwise, what can be done? What is when we have only battery to connect to such a load, which takes a current like this? The other possible thing what can be done is to make the battery or the chemicals of the battery slightly capable of giving this 12 amperes, wherein this requirement, this current requirement will only be for some millisecond duration. This time is only milliseconds. Then there is hours of 4 ampere current requirement. So only for this few milliseconds, we are actually increasing the capacity, current capability of the battery, C rating of the battery, which is also not a good engineering solution, right? So for such cases, this kind of a hybrid solution where this surge requirement can be given by the supercapacitors and then the nominal current is given by the battery is what we are proposing. Okay, it is already in use where I'll show many applications like camera. In a camera, the flash requirement is a surge requirement. Other requirements are all nominal. Okay, so when there is a flash, the current should flow from a supercapacitor, otherwise from the battery. So a hybrid kind of a storage can be preferred, right? Then what is other scenarios in which we can use that? A surge requirement by a motor. So one thing what we saw is during starting of an IC engine, when the IC engine starts, it takes, say, the nominal 12 volt battery which is used in a two-wheeler is having a current rating of say 2 amperes. Okay, so that is a nominal current which flows out of those batteries. But at the time of starting, it takes around 60 ampere current. So this is the current which it takes at the time of starting, and you can see that as a corresponding dip in the voltage of the battery pack, indicating that it is getting overused, for it is getting strained at that time, right? So this time is approximately only around 200 milliseconds duration, but then this value comes around 60 amperes, wherein this nominal current is only 2 amperes. Okay, so a battery which is 2 ampere rated is supposed to deliver 60 amperes for 200 milliseconds while it is delivering the starting power. That is why if you have experienced that the starter batteries may not last very long. For a two-wheeler, not more than 18 months to 24 months it will last. That is because of many such surge currents being drawn from those batteries. Okay, so in many such situations, when we go for a hybrid storage, so what we did next is just to make a hybrid storage without having any control. So what we did is just to have a supercapacitor. Then we had this 12 volt battery, and as I showed before, the starter connection was there. So already the battery was connected. So what we did is, so there was battery connected to the whole system and all. So what we just did is, we just connected a supercapacitor of the same voltage rating, which is charged to that same voltage, say 12 volt in parallel. Okay, and then try to start the two-wheeler. So what was observed is it was 60 ampere itself, but in that 60 ampere, the higher current, the more higher amount of current was actually, it was 60 amperes when there was only battery, but when we used both battery and supercapacitor, it took around 80 amperes. But in that, the 60 ampere current was almost supplied by the supercapacitors, and only around 10 to 15 ampere current was what was delivered by the battery. Okay, so naturally, when you connect the supercapacitor in parallel to the battery, because the supercapacitor is having a higher power density, it has a natural tendency of taking up the surge. But the sharing still imposes a current of 15 amperes on the battery, which is much, much less than 60 amperes, which was flowing before. And that is very good, actually. But then we don't want this also. If you want the battery life cycle to be very, very large, we don't want this also. We want it always to be around only 2 amperes. So in that case, we will require some kind of a control here, a circuit which we can control. Okay, so this is a natural way in which the current sharing happens when you connect the supercapacitor to the battery in parallel to a load which requires some kind of a surge current, such that the surge value is always given by the supercapacitor only. Okay, so after this time, when the IC engine starts, it is actually the current flow becomes negative. As you know, it will charge the battery or the supercapacitor, and that is also happening. So how we can make a hybrid storage is by having a control. So what is the control we need to have? Suppose I plus I dash is a current, where I dash is the surge current, okay, and I is the nominal current. So what we try to do is to connect a current source in parallel with a voltage source. Okay. Now, if the current source is always maintaining a current, the nominal current I to flow, okay, then naturally the other requirement will come from the voltage source. So that at this node, there is no violation for KCL. Okay. So when we use two storage units in parallel, one storage unit must be current controlled. The other storage unit must regulate the voltage. We can have both of them giving current, that is possible, but we cannot have both of them regulating the voltage. Regulating voltage can only be done by a single one, right? So, but then here what we see, the current nominal, the current the storage which does current control, or which makes a constant current to flow, if we make the nominal current to flow from that storage, then naturally the surge current comes from the voltage regulated source. Okay, so this is what we can see here. This is a battery and this is a supercapacitor. So here what we have tried is to use the battery with the converter which will control the current. So this converter is current control. Okay, and then we have supercapacitor where the converter will regulate this voltage always to what is required by the load. Okay, so that naturally the surge will flow from the supercapacitor. I hope you understood the whole thing. Okay, so this is the whole circuit diagram. It is a conventional bidirectional buck boost converter. It is actually having a boost in this direction and it is a buck in this direction. Okay, the other one also is a bidirectional buck boost converter. Both of them are parallel to the load, being the starter motor. Okay, and it is for a two-wheeler, it is a 12-volt motor which is there. Now this current, inductor current I, is controlled and regulated. Here this by properly switching these two switches, S1 and S2. And then S3 and S4 are switched to regulate this output voltage to 12 volts. Okay. So the first circuit, first buck boost converter is current controlled. The other one is voltage controlled. That is the only way you can do a hybrid structure. If you have many more units coming in parallel, there can be only one voltage regulation. All others can do current control. And this current control will help us to find out what is the division of power. If there is a total power of 100 watts, how much each of the source is going to deliver is what we can control by controlling the current. Okay. So current controlled things can be multiple, but there can be only one storage which will do the voltage regulation, and naturally that will deliver the surge. Okay. So I'm just trying to show one design of the current controller in between. I just wanted to know if you have any doubts regarding whatever is shared till now, because we are going to little something which is more technical now. Do you have any doubt? If you have any doubt, you can ask me. We can spare some 5 minutes now. So the doubts, the portions taken till now, where we have laid down the architecture of a hybrid kind of a storage.
Ma'am, can we have a single converter for battery and supercapacitor?
No, we cannot. Why? Because we need to control the current. We need to control. We are going to parallel them. We can have a single converter if you are thinking of a converter which has multiple input ports and a single output port. In that sense, we can have. Otherwise, we cannot have. It has to have two different free degree of freedom to control. We can think of a multi-input, maybe 12 input and so single output converter, utilizing some of the elements which can come in common, and that is possible. That is workable. But then we cannot have one single converter controlling both together. So, I mean, single port input and single port output is not possible. Dual input, solo output with 2 degree of freedom controller converters are possible. Okay.
Okay.
Anybody else?
Madam, instead of battery, fuel cell can
Yes. Yes.
make
It can be anything. Instead of battery, we can have fuel cells or maybe a flywheel based some generators. All those things, wind, micro wind turbines, any unit, any such things.
so all are like current controlled.
See, when we want a supercapacitor to deliver the surge current, it is best to have the other thing as current controlled. Otherwise, what we can do is we can make that as a base thing. It can regulate the voltage always. But then the supercapacitor current will have to be correctly given as the surge current shape. Okay, the current reference for the supercapacitor has to be very precisely given as the shape of the surge current, which may not be predictable always. So that is why the easiest way to do that is to do it this way.
Okay, madam, thank you.
Anybody else? Okay, in that case, we'll just quickly see how we can also design these current controllers for such a system. And the same method, which is shown now, can be used for the design of the voltage controller also. Okay, so when we see at the current controller, it is something which is going to make this error 0 as the time t tends to infinity. And that is the whole idea of having a controller, is to minimize the error, right? The error is the reference IL star being the reference value, and then IL is the actual sensed value. And a controller is designed such that this error will tend to 0. If it is E of t in time domain, it should tend to 0 as t tends to infinity. Okay. And the plant, this is the transfer function representation of the whole converter, which we call as a plant. So the plant transfer function is IL by D, so that if the controller gives the duty cycle as output and it is fed to the transfer function, it gives the current as the output, which can be fed back. Okay, so IL by D is a natural plant transfer function which is preferred to do a current control loop. If it was a voltage control loop, it was VFS by D, which is preferred. Okay, or sometimes it is VFS by IFS. If it is coming, the controller gives the current reference. Okay, fine. So the current controller, if you have a current reference, which is a sinusoidal reference, for instance, then how we can proceed with this is that we will convert the reference to the S domain. Try to write down what is E by IF, this E by IS transfer function, which comes out to be like this, where EFS is something like this. And then we will try to find out keep the transfer function as a PI controller, which is most preferred, and then try to find out what is limit S tends to 0, S into E of S. Okay, so it should tend to 0. This is our final value theorem. Limit t tends to infinity, E of t is equal to limit S tends to 0, S into E of S. Okay. So if the reference is sinusoidal, it will naturally not go to 0. So we go for other converters, other controllers like PI. It's a different scenario. Now we'll just see one way in which we can do the control here. Suppose this is IL by D cap transfer function we have for the converter. Okay. And the reference value what we have is constant DC reference with, say, a magnitude of A. So A into U of t is having a plot like this. It is a DC reference with a magnitude A. Okay. The Laplace of this is A by S. The Laplace of this is A by S. And then this IL, what we do is now, see, normally what people do while they tune a controller is they fix the shape of the controller. Say I say that it's a PI controller. So I say it is Kp plus Ki by S. I fix up that. Then try to tune what is Kp, what is Ki and all in order to get whatever desired output we want. Right? So sometimes you do it in a trial and error mechanism, and sometimes you do it with Ziegler-Nicholas method or many other schemes. But now what I'm trying to say here is a more generic way where I say that this is the reference A being a constant value, and what we want the output to be is something like this, which is an exponentially rising to this reference value, and the equation representation of that is A into 1 minus e raised to minus omega ct, where omega c decides the speed. So if I'm increasing omega c, we can see here that suppose I increase omega c, then naturally this becomes here. The speed becomes more. Suppose I increase it further, I can get it here. If I decrease omega c value, then naturally this graph goes here. So the speed decreases. The omega c decides the speed at which our output, the current, actual current, reaches the reference value. So by choosing a proper omega c, we can find out, we can draw what is the expected shape of the output. Okay, expected exponential rise of the output. Okay, now we take a Laplace of that, IFS, and that comes out to be this A by S into omega c by S plus omega c, where A by S is actually the reference. So we write that as a reference. Therefore, I by I star is coming out to be omega c by S plus omega c. Okay. Now from this block diagram, I by I star is nothing but this CFS into IL by D divided by 1 plus CFS into IL by D. You take that kind of thing. So this IL by D being a boost converter, and if you simplify it to an RL network, it comes out to be R plus LS, and this is how it can be written. Therefore, what you can write here is just compare omega c by S plus omega c to this and find out what is C of S. Okay, so C of S comes out to be omega c into Ls plus R by S, which is having a shape of a PI controller, right? Where the value of Kp is L omega c and Ki is R omega c. Okay, so that is naturally we get the values for the PI controllers for the current control. The same mechanism you can follow for the voltage loop as well, where the voltage transfer function can be used here, and then find out what is the natural way of shaping the keeping the controller. So here what we have done is a very generic mechanism. We have not fixed the structure of the controller. We have only fixed the response. Okay. Now, as I said before, the balancing is yet another issue when we come to a supercapacitor bank being used in such systems. So when we try to use a supercapacitor, this is small. This is around 2 volts only. For a 12 supercapacitor cells connected in series, and which was connected to around 30 volt, it was, you can see there is a huge difference in voltages across each cells, even though all of them were the same 2.7 volt 3000 farad supercapacitor cells. Okay, so then what we had thought of is to have a balancing scheme, which is an active balancing scheme. This kind of a connection, we call it as a matrix connection, and it's a buck boost structure with a coupled inductor. Okay, so it is being buck boost. Whenever you keep a duty cycle of 50%, it is going to naturally balance the supercapacitors. So that these are the modes of operations for various on and off cycles, which is there, and this way we can extend it to n number of supercapacitors by properly modularizing it. Okay, so we'll check the supercapacitor voltages. Based on that, we'll try to find out which switch has to be turned on and turned off, and then based on that, there will be the excess energy in the supercapacitors, which causes a higher voltage, will be transferred to the inductor core. From the inductor core, the energy flows to another supercapacitor, which is having a lower voltage. Okay, So because we are having a coupled inductor which shares a common core, for the benefit of that circuit is from any cell to any cell, the energy can flow. Okay. Then the power calculation for this converter is not the power which the circuit demands, right? This power is only for balancing, and it will completely depend upon how much energy we need to handle. What is the how much energy imbalance is there? Okay, so the largest imbalance in energy, that is one thing we need to think of. Another thing which will be required is how much time we want this energy to distribute. Okay, that depends. That tells us about the power. So the largest energy difference will be when C min V max square minus half C max V min square is the largest energy difference, and the power is this energy by time, where T is a balancing time, which we can fix. So suppose I'm talking about a fast charging, where I want the charging time to be, say, 1 second, then the balancing time should be at least only 1 to 5% of that. So it should be 0.01 second. Okay. But suppose I'm talking about a charging strategy where the charging time is, say, 100 seconds, then I can very well go for 1 second time for the balancing. So based on what is the charging time we want, we can fix upon what is the balancing time we would require, and based on that, the power of the balancing circuit has to be calculated. Again, for a very fast charging, the power of the balancing circuit is also going to increase, but it is not going to be very large as energy which is required, which will undergo this, or the imbalance energy is very less when we compare to the total energy of the bank. Okay. So this is when we give a 50% duty cycle. So there was an imbalance in the voltage, and then there was when so this imbalance in voltage is there, and when the balancing circuit turns on, it gets balanced. Okay. So this is with 360 farads. This is with 1 farad. Then this is 8 1 farad cells getting balanced, and then there is 8 360 farad cells. Then we have when we have a closed loop control, suppose we are sensing the voltages and changing the duty cycle accordingly, then the balancing becomes much, much faster than what was in the previous case, and that is what is shown here. Okay, when you compare the open loop and the closed loop, you can see here the open loop control takes this much time, say 10 seconds to balance in this case, but here it is just taking around 1 to 2 seconds to balance after the balancing circuit is on. So the closed loop kind of control is giving the benefit of a smaller balancing time, which is suitable for a fast charging. Okay, so thing was tested for the hardware, where 4 cells were connected in this way in the parallel in the matrix form, and there was an imbalance, and then when the balancing circuit was turned on, I can see here how the voltage is getting balanced. And this balancing circuit was also used along with the supercapacitor bank made on a vehicle, where the vehicle is running only with the supercapacitor bank. Okay, so thank you. Now, if you have any queries or any things to be answered, I'll be happy to do that based on whatever you have understood from this, or whatever you need to know regarding supercapacitor as a storage. Open for discussion.
So participants, please make use of the time to discuss your queries with the resource person. So ma'am, I think we can wind up since nobody
Okay.
is. So thank you, ma'am, for your wonderful session on hybrid energy storage systems. So the presentation was very insightful, which combined the strong research depth and practical relevance. And I think it was highly valuable to all participants. So, and we truly appreciate the time and effort you took to share your expertise with us. So, on behalf of the organizing team, we sincerely thank you. Thank you, ma'am. Thank you very much.
Thank you, sir, for this opportunity. As all the participants, you can even drop an email, or you can get my number from the organizers, and you can always just ping me whenever you have any doubts related to this topic, or any other which you feel like you can discuss with me. I'll be very happy to interact, and this way I'll also get updated about certain things which the researchers are doing in our country. Okay. So thank you so much for this opportunity. You can find my mail ID and phone number in the NITC website, or you can also get it from the organizers. Thank you. Sir, I'm signing off.
Yeah,
I'll
yes, ma'am, you
end the
can.
call.
Yeah.
Yeah.
So participants, please note tomorrow is our final day and the session will start at 2 p.m. So from 2 to 6 o'clock, we have sessions, and at 6, we have the voluntary function and feedback session. And you have to take one online assessment test, and the test is scheduled on 22nd. 6 p.m. All the details will be shared through the WhatsApp group. So thank you for joining with us. Thank you. Thank you very much.